finite dimensional subspace of V, then the perp of U perp is equal to U. In other words, if you take the subspace of what do you call the inner product space V, then the perp of the perp is equal to U. We already have shown in our previous theorem, or the first theorem that we proved about the orthogonal complement, is that U is contained in the U perp of the perp actually. So this is what we already know. So the only thing that we need to show is that okay, the U perp of the perp is contained in U actually, if you use subspace. So let's do that. Why this should be the case actually. Why this will be the case. Now, let's take an element from the perp of the perp actually. Okay, let's take an element from the perp of the perp, and I need to show that this element is also in what do you call U. Okay, this must be element in U. By the way, from the previous result, I can also write that since U perp is itself a subspace, so the V can be written as the the sum of U perp, direct sum of U perp and the perp of the perp actually. This is something that we know, okay, from the previous theorem that we just proved actually, that if you take any subspace then and consider its perp, their direct sum would be equal to the entire space. And we know that U perp is itself a subspace. So the perp of the perp and the direct sum of the perp of the perp and the subspace would be equal to the entire space actually. So this implies there exists an element in perp such that V minus U belongs to U perp of the perp actually. Okay, V minus U belongs to U perp of the perp. There exists a unique U actually. So this is what that unique U. And I know that V can be written as a sum of U plus what do you call V minus U. So it's an element. So U is an element from U perp and V minus U is an element U perp of the perp actually. Okay. My claim is that this V must be equal to the U actually. This V must be equal to the what do you call U. Claim is V is equal to U. If the V is equal to U and U is in U perp, that means that V is in U perp. No. Okay. All right, so I'm doing something silly. So let's take, so in order to show this, let's take an element from U perp of the perp actually. Okay. Now from the previous theorem, there exists a unique U from the U such that V minus U belongs to U perp, and of course V is equal to U plus V minus U. Okay, V is equal to U plus minus. So here is my claim actually. So I need to show, in order to show this inclusion, I need to show that this V must belong to the U as well. And my claim is that such a V must be equal to the U. Okay, such a V must be equal to the U. So now since U belongs to U, so therefore V would belong to U. And how can I show it? Take the inner product of V with V minus U. Take the inner product of V with V minus U. Now V is an element of U perp of the perp, and V minus U is an element in U perp, so this inner product must be 0. Because this is an element in set, and this is an element, the perp of that set actually, so this inner product must be 0. Now if I write this V as what? This actually U plus V minus U and V minus U, and I simplify this U V minus U plus inner product of V minus U with V minus U. Then what do I know about U? That U belongs to U, and V minus U is an element in U perp. So this is 0. And what would be this? This quantity is going to be equal to the norm of V minus U square. So this implies that the norm of V minus U is 0. This implies that V minus U is 0, and this implies that V equal to U. Now since V is U, what does this show? That V also belongs to. So we picked an element from U perp of the perp and shown that that element must be in U, and hence this shows that for a subspace, the perp of the perp is equal to the entire, what do you call, U. One interesting corollary to this result is this, that if you consider, maybe corollary to this result is that if U is a non-empty subset of, what do you call, non-empty subset of inner product space U, then U perp is not something new actually, or the U perp of the perp is not something new. This is really equal to the span of U actually. This is equal to the span of U. Okay, so the U perp of the U perp is really span of U. Why this should be the case? So from the first result, we know that if you compute the perp of the U and you compute the perp of the span of U, the both must be equal actually. So the first theorem about the orthogonal complement that we proved tells us that the perp of U and the perp of span of U is equal to this. Now if you take the perp on both sides, therefore the perp of span of U and its perp, the both must be equal. But span of U is a subspace of V. It's a finite dimensional subspace of V. So if it is a subspace of V, I know that for any subspace, the perp of the perp is equal to itself. So therefore, the perp of the span U, perp of the perp of the span of U is equal to the span of U. So this really proves the theorem actually. Now let's talk about an application of all this stuff actually. So we learned this stuff about the orthogonal complements. The question is, what is the use of it actually? So here's an interesting application of of this stuff. Imagine you have an economic situation, you have an economic model, okay? And when you have an economic problem, and when you are solving this economic problem, the model turns out to be a system of equations. So imagine Ax equal to B is a system of equation actually that models your economic situation. That models your economic situation actually, or any economic, for example, phenomena or the process. Now I know about this x, that this x is kind of representing my expenditures. Okay, so this x is kind of representing the economic expenditures, or these are the costs. Okay. Now this system can have a unique solution. So if it has a unique solution, then it is kind of a fixed actually. So you can't have some other cost. So you have a fixed cost actually. But if this system is consistent and has infinity many solutions actually. So in other words, for x you have a lot of options actually. Okay? So for x you have a lot of options. So in other words, for expenditures you have a lot of options. You can have a lot of expenditures actually. A lot of vectors that represents your expenditures. But what would be you interested in actually? You always want to minimize the expenditures. Question: can we find a solution of a system in such a way, of a consistent system obviously, in such a way that this x is kind of a minimum, or its norm is minimum actually? Okay, its norm is minimum. So the topic that that I would like to do next is the minimum norm solution of a consistent linear system. Okay, so this is what that I would like to do. Okay, and for example, if we have some criteria through which we can find a solution of, so if it is a consistent system, it must have a solution. And the solution could be unique. In that situation, we can't do anything. But the more interesting case would be that when the solution has infinity, this system has infinity many solutions. The question is, what x would give you? What would be the x whose norm is minimum, okay, and still solve the system actually? Okay, so that can model, for example, all those situations where you want your x to be expenditures, and we want our expenditures to be minimized actually. We don't want to go them explode actually. Okay, so this is what really is the thing that I would like to do. So we will start with the definition. We'll start with the definition. So consider a matrix that is say an m by n matrix with entries from the field, which can be real which can be real number or complex number, and let y is an element in the column space of A. Okay, And I hope you remember the column space of A. So in other words, take the matrix A. So obviously the matrix A is going to have n columns like A1, A2, and An. What do you mean by the column space of A? Column space of A is the span of these vectors actually. A1, A2, An. Span of the columns of the matrix A. So this is what is the meaning of the column space of A. Similarly, you can also define the row space for the matrix A. So when I'm saying that Y is in the column space of A, that means that Y is a linear combination of the columns A1, A2, An from A. This is what I mean by the column space of A. I hope that you remember it from your first course, otherwise this is what the definition of it is. So consider a matrix A, and Y is a linear combination of the columns of A. So it's in the column space of A. Then a solution S, okay, of vector S of a consistent system. So take a consistent system, say Ax equal to Y, okay, is minimum norm solution, of this system, if S, the norm of S is less than or equal to the norm of any solution of U actually, where U is a solution of, what do you call, so for all U, where for all U satisfying AU equal to 1. Okay? So S is going to be the minimum if its norm, okay, is going to be less than or equal to norm of the all other solutions of this system actually, of the system that you have. Then you're going to say, okay, this is the minimum solution actually. The question is how to compute this minimum solution actually, okay? And obviously this can help us in, for example, such economic situations or any kind of situations where you have your model is minimum, is a system of equation, and you want to find a minimum solution to that system actually. Okay. Here's a little lemma that will help us, a little bit ahead of this. So if V and W, or maybe let T is a linear transformation from an inner product space V to inner product space W, okay, be a linear transformation where V and W are finite dimensional, So here's an interesting thing. Then you can do this interesting thing. So what is that interesting thing? The kernel of T, okay, the kernel of T is equal to the perp of the range of T star. So compute the range of T star and compute its perp actually. Okay? compute its perp. that would be equal to the kernel of T. And similarly, the range of T is equal to the kernel of the adjoint of T and its perp. Okay, the range of T is equal to the kernel of adjoint of its perp actually. Okay, this is what an interesting result is actually. So here's a proof of it, and then I'll formulate a theorem that will, give us solution to this problem actually. Okay. So let's take an element from kernel of T. Okay. This is going to be true if the T of V is 0. Now, if the T of V is 0, that means that T of V W is equal to 0 for all W in W. Okay, in W. And if this is the case, then by the definition of adjoint, if you take this T on the other side, you're going to have V T star of W equal to 0 for all W in W. So what does this show? This shows that, by the way, T star of W is an element in W. It is in the element of the range of T star actually. And V is orthogonal to an element that is in the range of T star. So I would say this means that P belongs to the perp of the range of T star. This is what precisely it means actually, that they take an element from the range of T star, which would look like this, and V is orthogonal to it. Okay, and V is orthogonal to it. So what does this show? This shows that the kernel of T is equal to the range of T star. Okay. Similarly, you can also show this very easily, so I'm not getting into it actually. So, maybe this is an exercise for you to show. Okay, this is an exercise for you to show. So what does this show? That if T is a linear transformation from kernel of T to range of T star, T from V to W, then the kernel of T is the range of adjoint, kernel of T is equal to the perp of the range of adjoint, and the range of T is equal to the perp of the kernel of adjoint actually of T. Okay. Now what are the consequences of this actually? Okay. Now take in particular in this result V equal to say Fn, where the F could be Rn or Cn. Okay. And take W to be, what do you call, Fm. Okay. And consider a matrix that is an m by n matrix with the entries from F. Okay. So it's an m by n matrix with entries from F. Then we know that every matrix induces a linear transformation actually. Okay. So this matrix will induce a linear transformation TA from V to W. Okay, where the V is Fn and W is Fm actually. In other words, PA operated onto a vector U from V is equal to what? The matrix A multiplied with V. Okay? Where the matrix A multiplied by V is a vector in W, in other words, Fm actually. So if it is m by n and V is n by 1, this would be a matrix, and this would be a vector m by 1 actually. So you're going to get Fn actually. Okay? So TAV is equal to T. Now, what is the null space of A? Okay, remember some of the terminology from your first linear algebra course. So what is the null of the matrix space matrix A? So the null of A consists of those vectors from, say, V such that a V is equal to 0. A V is equal to 0. In other words, it consists of those vectors from V for which the TA operated onto V is equal to 0. So this means that this is really the kernel of TA. Okay? The kernel of the linear map TA. But this result tells me that the kernel of TA is the range of T star perp actually. Okay? So this is equal to what you call range of TA star perp. But what is the range of T star A perp actually? The range of T star A perp is actually going to be the column space of A star perp actually. Because the range of TA star A, so if you write it a bit explicitly, the range of T star A is collection of the T star V, where the V are not from it's the T star W, where the W are from what you call space W, because because think about it. W, maybe I write TA. W, the adjoint, if the T is a linear transformation from V to W, the adjoint is a linear transformation from W to the V actually. So this is what is going to be the range of W. But this can also be written as A star W, where the W are from W. And this is what really is the column space of A star actually. Okay, so A star W is a vector, okay, in what do you call V, okay, and you can show actually that basically this is equal to the column space of A star. So hence the null of A is equal to the column space of A star. So this is what is the thing that I would like to say and show. Okay. Let me check it that if it is still working. Yes, it is still working. Okay. So what did we show? That null space of A is really equal to that you take the column space of the conjugate transpose of the matrix A and consider its perp actually. Okay? Consider its perp.